Hi everyone, welcome to the third lecture of this 6th week course where we were discussing the temperature sensors. We are discussing the course on microsensors and nanosensors. In the previous class, the lecture 2, we have discussed the thermistors, particularly the PTC thermistors. If you remember, we have seen two different type of thermistors. One is NTC and another is PTC. PTC is the positive temperature coefficient thermistors, where the resistance rises with respect to increase in temperature. Okay, NTC is just reverse of that, means the resistance drops when the temperature increases. Okay, and if you remember, these were the symbols of NTC and PTC thermistors. Okay. Then we have also seen that NTC thermistors are typically made up of ceramic materials, metal oxides basically, which are sintered at high temperature. Some of the common oxides that we have seen for NTCs were manganese oxide, nickel oxide, cobalt oxide, copper oxide and iron oxide. Right. So these were oxides which can be transformed into different shapes and sizes for the development of NTC kind of devices. Okay. The advantage of this NTC thermistors are its high sensitivity. These NTCs are usually have more, higher sensitivity as compared to their counterparts like PTC as well as the RTDs. Okay. They can be miniaturized very similar to the PTCs, and the process is compatible with CMOS fabrication processes as well as with the MEMS technology. Okay, particularly if you see the fabrication temperatures of these NTCs are favorable for the current existing MEMS technologies. Okay, just have a look on this graph where I have shown the resistivity versus temperature curve of a thermistor. It can be one of the oxide, say I am calling it metal oxide. Okay, MOX. It can be a typical say iron oxide or manganese oxide. Okay, on the same plot I have plotted the resistivity curve for platinum with respect to temperature, and the x-axis is from minus 100 degrees Celsius to around 500 degrees Celsius. So the resistance temperature characteristic of these two different devices, platinum I am showing to compare it with the RTDs. If you remember, we have seen that platinum is the base material for any kind of RTDs. Okay. From this graph, we can compare the characteristic of a thermistor and a RTD. Okay. If you see this carefully, just have a look on the drop in the resistivity for thermistor, which is from around 10 power 5 to somewhere here 10 power minus 2. Okay. So between this minus 100 degrees Celsius to 400 degrees Celsius, a thermistor changes its resistivity from a factor of say 10 to the power 5, okay, to 10 power minus 2. Okay. So if you see, the total change is around of the order of 10 power 7. Okay. But at the same time, if you see this change in the resistivity of this platinum, which is changing its resistivity from say 10 power minus 5 to 10 power around minus 6. Okay. So the change is about of the order of say 10 times or so. Okay. Here if you remember, it is 10 power 7 times, it is of the order of 10 times. Okay. You can see the clear difference between the resistivity drop for this huge temperature range for a RTD material, which is platinum, and a metal oxide, which is the building block for a thermistor. Okay. So the thermistor have high sensitivity for the measurement of temperature, particularly if you talk in this temperature range of minus 100 to 400, or typically saying minus 100 to 250 degrees Celsius, they have edge. Okay. So mostly you will find that simple devices, say for example a coffee mug. Okay, it is installed with the NTC kind of devices. Okay, for temperature monitoring. However, the characteristic of these thermistors are highly non-linear in nature. Okay, but again, if you remember the first module, we have discussed that let it be nonlinear, we can do always a piecewise linear approximation for all these nonlinear sensors. Okay, therefore can imagine that over a small temperature range, okay, say if I consider, I have given an example of say water heater. Okay, usually you want the temperature to be monitored very precisely from say 85 degrees Celsius to 99 degrees Celsius before water actually boil. Okay, or say 80 degrees Celsius to say 100 degrees Celsius or so. Okay, so you have a very narrow range of temperature where you actually want to monitor the temperature. Okay, so in this small range you will find lot of entities to provide you a transfer function which is pretty linear. Okay, therefore for a limited range of temperature, the resistance of thermistor, particularly for NTCs, okay, you can write it as R naught equal to R theta naught into 1 plus alpha theta naught into del theta, where the del theta is the temperature difference. Okay, so you can imagine it to be linear in small temperature range. Alright, there are several mathematical models of a thermistor transfer function that exist in the literature. Okay, these models are basically based on approximation. More is the complexity in the equation. You can understand that more has been complexity associated with the approximations. Okay, in general, simpler the model, the lesser the accuracy you can expect. Okay, and calibration and the difficulties to use this thermistor increases for the complex models. Okay, so please note that all existing models are based on experimentally established relationship that establish a relationship between a logarithm of a thermistor's resistance, say S, okay, and it relates to its absolute temperature T by one polynomial which gives ln S is equal to A naught plus A1 by T plus A2 by T square plus A3 by T cube, where A naught, A1, A2 and A3 are constants. Okay, so all the approximation that you see for these thermistors are approximation for this particular polynomial which relates the thermistor resistance S, in fact ln of this S with the temperature T. Okay, so the beta coefficient, if you remember, or the alpha one that you have seen, all are derived from this particular equation which suggests the relationship between the resistance and the temperature. Okay, so from this basic equation, basically three different computational models has been proposed over the time. Okay, there can be other models also, but we are limiting ourselves to these three models, although we will see some more simpler models in the coming slides. Okay, the simple model suggests that the relationship between T and S as T is equal to 1 by T naught plus ln S by S naught divided by beta and whole inverse. Okay, this is the simplest model. It is known as basically a simple model. Okay, then you have a Fredon model which suggests this resistance S is equal to S naught into e to the power beta into 1 plus gamma into T minus T naught, and then you multiply it with 1 by T minus 1 by T naught. Okay, then the third, which is very popular, which is known as Steinhardt model, which suggests temperature to be equal to alpha naught plus alpha 1 into ln S plus alpha 2 into ln S square plus alpha 3 into ln S cube and whole inverse. Okay, this is the Steinhardt model, and deriving from this there are some more version of this particular equation. So an individual thermistor curve can be closely approximated through one more equation, which is 1 by T equal to A plus B log to the power to the base E into R plus C into log to the base E R whole cube. Okay, where this T is the temperature in Kelvin, R is the resistance of the thermistor, and ABC are the curve fitting constant. Okay, this equation is actually another version of, you can understand, another version of equation 3 over here. Okay. Then a simpler equation can also be derived, which suggests that this temperature T is equal to B by log to the base E into R minus A minus C, where A, B, C are found by selecting 3 R and T data points and solving these 3 resultant simultaneous equation. Okay, so this can be another version of thermistor temperature resistance relationship. Okay. Another simpler relationship that has been discussed in the literature is RT is equal to A R naught into e power B by T. Okay, where RT and R naught are the resistance of the thermistor at temperature T and at ice point. Okay, so R naught is the temperature at the ice point. Okay, so this is another version of equation. So what we have seen that this is the equation of thermistor ln S equal to A naught plus A1 by T plus A2 by T square plus A3 by T cube. Various models has been proposed based on this polynomial and using various various approximations. Okay, approximations to find out this A naught, A1, A2 and A3, these 4 are different constants. So to simplify this, various approximations has been made, and based on the approximations you have different models, like I have discussed the simple model, Freden model and Steinhart model. The simple model suggests that this T is equal to 1 by 1 plus T naught plus ln S by S naught by beta. Okay, or 1 by T naught plus ln S by S naught by beta whole inverse. Okay, similarly Freden model is also simpler as compared to the polynomial that we have seen. Okay, it doesn't have any T to the power 3 values. Okay, so S is equal to S naught into e power beta into 1 plus gamma T minus T naught, and then multiplied with 1 by T minus 1 by T naught. Okay, Steinhart model is another way to approximate the polynomial that we have seen, where T is equal to alpha naught plus alpha 1 ln S plus alpha 2 ln S square and plus alpha 3 into ln S cube and whole inverse. Okay, then we have seen that we can write this equation through even more approximated way, where we can write that 1 by T is equal to A plus B ln R plus C ln R cube. Okay, where T is the temperature in Kelvin, R is the resistance of thermistor in ohms, and then A, B, C are different constants. This equation is of course derived from the Steinhart model. Please note that these values has been calculated based on various approximations. Then another simple equation that we have discussed is simple T is equal to B by ln R minus A minus C, where A, B, C are again found by selecting 3 different R and T data points and then solving 3 resultant simultaneous equations. Okay, so you have 3 RT values, R1 T1, R2 T2 and R3 T3. Okay, and if you solve these 3, you can actually find this ABC value, and then finally you can calculate the T value. Okay. Then one more relationship that we have seen was RT is equal to A R naught into e power B by T, where RT and R naught are the resistance of thermistor at temperature T and the R naught is at ice point. Okay. So these approximations are very crucial for thermistors, and we have to see that in which case which thermistor, which equation fits better for our thermistor. Alright. So all these equations has been derived thinking that there is these thermistors are zero power resistance, means it is not consuming any power and there is no self-heating particularly for these thermistors. Okay, so when a thermistor is used as a temperature sensor in a circuit, its all characteristic is assumed to be based on zero power resistance. Okay, so this means that the electric current passing through a thermistor doesn't result in significant temperature increase, which can affect the accuracy of the measurement. Okay, so all your calculations are based on the fact that you have assumed that these thermistors doesn't consume any power, means there is no heating or there is no self heating in this thermistors. We call it zero power resistance. Okay, but that is not always true. Thermistor will, of course, it's a, if you remember the definition, we have seen that thermistors are thermal resistors, or the resistances which changes its value with temperature, right? So of course it's just a variable resistor which is changing its value with respect to temperature. Okay, so it can't be a zero power resistance. Okay, it will have some self-heating effect. Okay, so a static temperature increase in a thermistor due to self-heating is governed by this particular equation. TH is equal to R into N square V square by S, where R is the thermal resistance to the surrounding for this thermistor. V is the applied DC voltage during the resistance measurement. S is the resistance of the thermistor at a measured temperature. Please note that R, the small r and S are different. R is the thermal resistance to the surrounding, while S is the electrical resistance of the thermistor at a measured temperature, and N is the duty cycle of the measurement associated with any AC signal. For DC measurement, N you can take as 1. Okay, so to use a thermistor practically, its transfer function must be accurately modeled. When I say transfer function, means its resistance, which of course depend on the temperature. So resistance versus, or resistivity versus the temperature, that data you should have. Okay, so this function is of course highly nonlinear and generally unique for each thermistor. Okay, so if you go through the specification sheet of a thermistor, even from the same company, you will find that their transfer function is very unique. Okay, so analytical equation between the resistance and temperature is highly desirable, particularly it doesn't follow actually any law. So every thermistor will have its own basically transfer function. Okay, so you should always know the transfer function associated with this thermistor, then only you will be able to utilize it in proper manner. Okay, so generally the NTC thermistors can be classified into 3 major groups depending on the fabrication method or its shape and size and other form factor considerations. Okay, it can be a bead type thermistor, it can also be a chip type thermistor, and sometime you can obtain this by depositing on some substrates. Okay, so let us see what is bead type thermistor very quickly. The bead, you can see schematic diagrams for bead type thermistor. I think from this diagram things would have been clear to you. The bead may be bare or coated with glass, epoxy, or encapsulated into a metal jacket. So these beads are nothing but the ceramic material which is acting as a NTC. If you remember, I have just mentioned that these NTC thermistors are some common metal oxide based material like iron oxide, manganese oxide, etc. Okay, so this you can deposit them in a shape of bead. Of course, you should have lead for proper contact. Okay, so this bead is not bare beads, they are actually coated with glass, epoxy, or they are sometimes encapsulated into a metal jacket depending on for what application you are using it. Okay, this kind of coating not only help in in this encapsulation, but it also help to make the device very rugged, and it allow the devices to be used in harsh ambients. Okay, so usually the glass coated or glass encapsulated these thermistors are very rugged in nature. Okay, but then you can understand that metal jackets are also very strong. Okay, so all these beads have usually this platinum alloy lead wires, these one I am talking about, which are sintered into the ceramic body at again very high temperature. Okay. Then you have chip thermistors with surface contact for lead wires. You can see a block kind of material on which some blackish metal oxide has been coated. Okay. So generally here the chips are fabricated by some tape casting processes like subsequent screen printing, spraying, painting or vacuum metallization of the surface electrodes. Okay. The chips are either bladed or cut into the desired geometry which is required. Okay. Then another is by depositing on the substrate. Okay. So the semiconducting materials are deposited on a suitable substrate. The substrate can be glass, alumina, silicon, etc. And these thermistors are preferable for integrated sensors for a special class of thermal infrared detectors. Okay. And the deposition is done by various methods. I think there are another courses dedicated to only the deposition. Usually this deposition is done by either some chemical process. Okay. These depositions for fabricating these NTC thermistors are either done by some chemical process, okay, or by some physical process. Okay. Physical process. Okay. For chemical process, you can understand it by some chemical bath depositions. Mostly this chemical bath depositions, you will find the thermistors. This chemical bath depositions can be helpful for developing some R&D kind of thermistors, but for the commercial level, usually you use, this is CBD. For commercial usage, you use CVD, which is chemical vapor deposition. Okay. So usually chemical vapor deposition techniques are used for developing this NTC thermistor, where the semiconducting materials are deposited on suitable substrate. CVD can be of various type depending on the precursors used and the heating method used. Okay. You can have a hot wall or cold wall CVDs. You may also have, depending on the chamber, the CVD chamber, the walls of CVD chambers are how they are heated. Okay. You can have PECVD, plasma enhanced CVD. Then based on precursor, you can have say MOCVD, that is metal organic CVDs. Okay. I mean, then there are different CVDs based on pressure. So you can have atmospheric pressure APCVD, atmospheric CVD systems where the deposition takes place at atmospheric pressure. Then you may have LPCVD where the deposition takes place at lower pressure, right. So there are a number of methods for the deposition of this semiconducting material to fabricate the NTC thermistors, right. For physical processes, usually in laboratory, people may use thermal evaporation or sometime E-beam evaporation. You may have some advanced level of physical deposition processes like sputtering. Sputtering can be of various types. Okay. It can be say RF sputtering, DC sputtering, etc. Okay. What I mean to say that this kind of fabrication technique is very popular for obtaining NTC thermistor where the desired semiconductor film is deposited at the exact positions where it is required. Okay. So these are mostly popular when you want to have on-chip NTC thermistors, particularly I am talking about the electronic ICs, okay, where you can do this deposition processes in line with the current MEMS technology. Okay. Typical characteristic of this NTC thermistors are their temperature range is typically around -55 degrees Celsius to 150 degrees Celsius, or you can understand as -100 degrees Celsius to +250 degrees Celsius or so. But the good thing is that their beta value is very high. When I say beta value, I want to say the relationship between the temperature and its resistance. Okay, so since beta value is high, means the slope is steeper. Okay, means that the sensitivity is high. Okay, the response time of this NTC thermistors are really quick. Okay, you can expect it to give response within single second. Okay, which means that these devices are very fast. Okay, and that's why I mentioned initially that NTC thermistors are very popular as compared to other temperature measurement devices. Okay, and good thing about these NTC thermistors are although they are made up of ceramic, but you can also make this NTC thermistor using silicon, because silicon itself is a, it has a characteristic of semiconductor. Okay, and typically being a semiconductor, it has a negative temperature coefficient of temperature. Okay, so you do not have to make any extra arrangement to have NTC. Okay, it has originally negative temperature coefficient of resistance. Okay, therefore the silicon NTCs are also very popular, and even it can have smaller form factor as compared to the ceramic NTC thermistors. Okay, so although the ceramic NTC thermistors are very small, okay, it may have a form factor of around 1 millimeter square, but the silicon based NTC thermistors may have even a form factor smaller than 1 millimeter square. Okay, so if you want to design a new NTC thermistor, the design consideration that you can have are the form factor, because you have to understand that for what application you are developing this NTCs, what should be its size, what should be its shape, and all those things. Okay, then power dissipation versus self heating is another important thing to be considered while designing these sensors. Okay, then packaging of these thermistors are very important. As I have mentioned earlier that the glass encapsulated say NTC are very rugged in nature, but your requirement may be of chip on board. Okay, so that's what I am mentioning, that the packaging you have to consider initially while designing these sensors. Okay, then what calibration technique you are going to use for this NTC thermistor has to be understood while designing this sensor, and of course the EMI RFI shielding is very crucial for this kind of devices. Okay, then there are different challenges and limitations associated with this NTC thermistor, particularly the silicon NTC thermistors. The important challenges are it has narrower temperature range when you compare it with some of its counterpart like thermocouples. Okay, then aging and drifting is very common among these NTC thermistors. Okay, and it may have effect of the thermal cycle. Okay, so if you have if you have expose your device for various cycle from say minus 100 degrees Celsius to 450 degrees Celsius or so, you may find that effect on your device. Okay, then calibration complexity at high precision level is another disadvantage or challenge, I would say, associated with this NTC thermistors. Okay, and nowadays when you are talking about flexible sensors and other kind of wearable devices, the flexible and stretchable NTC sensors development is of great interest, and then there are various challenges posed at that particular front, particularly associated with the semiconductor ink that has to be printed by the current existing technologies like say inkjet printer or say plasma jet printer technologies. Okay, so these are some challenges, but then of course these can be overcome by choosing the suitable material and suitable substrate and using the correct measurement parameters. Okay, so with this we are finishing this thermistor including both PTCs and NTC thermistors, In the next class, we will discuss thermocouples. Thank you.